Hello, my name is Rob Knapp, and I'm a developer at Wolfram Research who works on numerical computation. And the thing we've done the most recently is a whole series and suite of functions that do convex optimization. So one question you may have is, why is convex optimization interesting? Well, I'll sort of give it in a little bit of a historical perspective. So back in the 50s and 60s, people started, and even earlier, people started using linear optimization to try to solve various problems. And then there were some advents of some algorithms, particularly the simplex method, which is well known. And that allowed people to solve much larger scale problems. And as soon as that sort of came online and became something that was readily available, people started using linear optimization for industrial strength tasks. I mean, all over the things like airline scheduling, optimization of all sorts of things. And so it became sort of a tool in essentially an engineer's toolbox. It was a really important tool to be able to do things. Now, more recently, sort of in the late 80s and early 90s, some people figured out that they could do something called convex optimization, which is linear optimization, actually a special case of that. And the idea is if you have a convex set, and one of the things that led to this was the interior point methods for linear optimization. The simplex method worked great for smaller size problems, but for really large problems, people discovered interior point methods worked really well. And that led to this development of these convex optimization ideas and methods. And it turns out that a lot of the same things that were done with linear optimization can be done for convex sets and nonlinear convex functions on nonlinear convex sets. So that generalized the whole thing. And sort of it's just recently in the past 10 to 15 years that people are starting to take that up. Now the algorithms are a little more complicated than linear programming algorithms or linear optimization algorithms, but they still allow for fairly large scale problems and industrial strength use. And the number of applications that you can do with these is just hugely expanded from just a linear case. Not surprisingly, because a lot of real world problems do end up being nonlinear. So what I'm going to do is I'm going to go show you through today some of the functions that we've developed and some of the features we've added to the Wolfram language to make modeling for convex and actually including linear optimization more readily available. So there's a whole bunch of points. And in the examples I'll go through, we'll show a lot of these points, and I'll be emphasizing a few of the things. Some of the language features will be emphasized as well. So I'm going to get, rather than sort of talking generalities, I'm going to get down to working through these specific examples and showing you sort of what are new features and what's enhanced, what's different. So let's start with a nice, simple, understandable problem. So the classic fit to data is to minimize, ax or a lambda minus b with a 2 norm. That's the classic least squares fitting. The problem with least squares fitting is it can be quite sensitive to outliers because the square norm is intolerant to big deviations. Those become very big. So the idea is you can get something that's more robust to outliers by using a 1 norm. And so that's actually turns out to be a very simple a linear optimization problem, and we'll show you how it sets up with our current new modeling scheme. So first we've got some data, and here there's a few outliers which cause problems for a least squares fit. So what we're going to do is we want to fit this with a basis of sinc functions. So these are functions that look like this. So first we create a design matrix. There's a design matrix command in Wolfram language. Okay, we consider the response, which is the y version of the data. So this is just a one-dimensional fit. Okay, so now here's where we get into some new language features. So we want to minimize the 1 norm. So that means that the sum of the absolute values of a sub I is less than I. So we can actually write for each component, we can introduce a new variable, s, and minus s is going to be less than that, and that's going to be less than s, and the s's are going to be positive. So that sort of bounds the absolute value. We introduce a new variable. Now, we could write an inequality for each of these terms, okay, for each component of the data. Okay, but instead of doing that, this new language feature we have, which is, this is an example of vector less equal. We have vector greater equal and vector greater and so on and so forth too. These allow you to specify inequalities as a vector all at once. And that's actually a really nice new language feature that allows modeling much larger scale problems much more easily. So here we just say S is going to be a vector, okay, and minus S is vector less than A dot lambda minus B is less than vector less than S. And notice that this inequality sign is a little bit curved. So it's different than the standard less than or equal to sign that we have here for the scalar inequalities. And that's what, so there's an actual full form which you can type out, but often I think you'll just want to use this notation with this vector less than or equal to. Okay, so we can add the S sub I, so we're minimizing the S sub I, the sum of the S sub i's. We can represent that with total. So the modeling thing basically becomes, we write the objective as the total of all the S's. That's equivalent to the one norm by this transformation we've done. We can put in parameters, and those are put in with the constraints, and those are explicit when they're explicit values. And then we have two variables, lambda and s. S are the introduced variables, and lambda is the actual fit coefficients that we want to get. So we can find the result, and then what we can do is we can just, so the result is given in terms of rules for these variables. So it'll be lambda goes to something and s goes to something, and those will be vectors. And then we can just put in basis dot lambda. Notice lambda is going to be a vector variable, so that'll replace, and that's the actual version of the fit. And here's a comparison between that and the least squares fit. So as you see, the least squares fit, where those outliers are here and here, it's tending to go way up higher than is necessary. So that's the advantage of an L1 fit. Notice that you can actually do this directly using the Wolfram language function fit, and it just works. So this is the least squares fit as the default, and we can say the norm function want 1, and we just get it. So this is something where we've used sort of the convex optimization to implement something through another algorithm function. Okay, so let's go on to the next example, and that's data classification. For sort of the linear cases, is awesome. Simple case, linear case is often called like a support vector machine in machine learning. This is sort of a more general case of that. So suppose we have two sets of points, okay? So set 1 of points, set 2 of points. And now what we want to do is we want to find some polynomial, not just a linear polynomial, which would be a line, but we're going to find some general polynomial of some degree that's going to separate such as those 2 points of set, so that P of X is positive for one set and P of X is negative for the other set. So again, we don't have a size on the restriction of P, so we rescale the problem to require P is greater than or equal to 1 and P of X2 is less than or equal to -1. So the only trick we have to use here is 0. Since mathematics is very rigorous mathematically, 0 to the 0 gives sort of a special case, and we want that just to be 1 in this case, okay? Because that's like, when the power of a polynomial is 0, we want that coefficient 1. So we sort of write a special power function. So now here's a function that's a polynomial of degrees. So basically, this is just the definition of polynomial, but I'm using this p power function instead of my, the standard power function to avoid the problems with 0 to the 0. And then the variables are going to be the coefficients, the a sub ij. So here are the coefficients in the polynomial. These are my variables, so that's what I would fall for. And the constraints are the ones we did above. Okay, so for example, suppose we said we wanted quadratic polynomials. These would be the constraints, given those particular sets of points. So the first problem is to find out what degree polynomial can we do the separation with. So if you try, say, if I tried this with quadratics, with the particular sets of points I have, it would prove to be infeasible. So linear optimization will tell me whether it's feasible, namely, can the constraints be satisfied by any values or not? And if it's not feasible, then I need to up the degree. So what I do is I do an iteration where I limit the degree so I don't go sort of out of bounds. And then I just do this iteration, increasing the degree until I find a case where the thing is feasible. And then once I find a degree that's feasible, I actually find the polynomial that fits. And here's a plot. So one set is marked in red, the other set is marked in black, and the regions blue and white show the p less than or equal to 0 and p is greater than or equal to 0. So that's the classification problem. So that's sort of a generalization over the support vector machine idea. Okay, so here's another linear problem, and sort of what we've both languages has had linear programming for ages. Something we've done is we made part of what we've done is we made the interface much more convenient. Before, with linear programming, you had to enter matrices, you had to figure out what the matrix would be, enter that, and that could be a little bit tricky. I mean, when I do that by hand, I always get the signs of something wrong, and then I have to go back and figure out what it is. So this allows you to enter it in a much more intuitive language, and I think the last couple of problems have indicated that. So here's a problem. We're setting up a fairly complicated setting. I'm not going to go into the details of this. The idea is we're going to have a truss on a wall. We're going to have some anchor points. Okay, so these are the anchor points here. And for any given node, we set up a grid where the trusses can meet. In any given node, we consider the connectivity to neighboring nodes. They consider another force, and we're applying a force here. So this is the connectivity pattern is indicated in the red. So now what we do is we sort of set up constraints based on that connectivity. And something we're using here is we're using association to do fast lookup between the actual node and the connected nodes. And eventually we figure out the links. When we do this in a crude way, we get duplicates, so we don't want to add duplicate links as constraints. So we get the links. Eventually, you get a matrix. You put in a force balance equation, so the force has to be balanced. And with once you get all these constraints together, I can't really go into the details here because it becomes too detailed. But basically, we come to a linear optimization. We have objective, bunch of constraints. Okay, here are positive constraints on a part of it. That are easy to read. We do linear optimization. We get a result. And here's a graphic kind of indicating where the results. These are where the actual truss links need to be. So these are the ones that are non-zero, and the blue shows ones where the link are being compressed, and the reds and oranges are where it's actually pulling on it. So it's so I think that's a nice example of you can set up a modeling with a language. It's still complicated to set this up, but compared to actually having to write matrices, this is much simpler. Okay, so now let's look at an example of something that's a new function, linear fractional optimization. We did solve some linear fractional optimization problems through and minimize before, but the setup was not nearly as straightforward as it is now. So linear fractional optimization is really useful when you want to sort of minimize the ratio of two things. So in this case, what we're going to do is we're going to minimize the cost to profit ratio, because we want profit to be as big as possible and cost to be as low as possible. So if we minimize the ratio, we're sort of getting an optimal relationship. And notice that these are being set up as vector inequalities. So we put in constraints based on the demands, and so now we're considering here the cost of transporting electricity. I'm missing the graphic there, and we want to put in a couple power plants, and so we eventually do a linear fractional optimization problem with the ratio of cost to profit. Okay, we sort of set up constraints. And notice here, this is something that's sort of a language feature new, is that X is going to be a matrix. So in essence, the X that we get out are the entries in this matrix that show the solution. Okay, so X is actually, so you can have matrix, you can have vector variables, you can also have matrix variables too, which is very convenient in something like this, where we're talking about a grid of cities and a grid of plants, and we want to optimize. And this, of course, could scale up to whatever size you wanted. Okay, so now we're going on to some newer functions, and this one shows how you might use our quadratic optimization function. So this is it's quite a simple problem. So suppose you have two convex polyhedra, and these can be represented as mesh regions, or a way to generate a convex polyhedron is you can use the polyhedron package, or you can just take a set of points in, say, 3D. 2D would work as well, and there's a function called convex whole mesh that'll create a mesh. And so the inputs here are actually, these two regions are meshes. Okay, they're boundary mesh regions from our geometry project, and our optimization automatically processes these into equivalent linear inequalities that can be used. So the input becomes quite convenient for doing this. And all we want to do is we want to minimize the norm squared, which is a quadratic function, so it should fit in quadratic optimization. And so the problem comes in. And another point I'll make, which is kind of new shown in this problem, is I'm giving, instead of just getting a single solution out, okay, I can get properties of the solution out. So here I've asked for the primal minimum value, and that actually gives me the distance, the square distance. Okay, and I can also get the primal minimizer rules, which are the variable rules, and this is what the default output is that I've kind of shown you before. And it gives you the rules, which give you what the values of variables that gives that minimum value. Now, there are some other properties, and this is a big advance from before, is we can also, before, we didn't really have a way of getting out dual properties from a solution, or a nicely documented way. But now you can also get something called the dual maximum value. And there's also a constraint sensitivity that shows you how, uses the dual to show you how sensitive a solution or a minimum is to constraint. So being able to get the dual out from optimization functions is one of the big new features. Okay, so here's an example that again is quadratic optimization. So what we're doing is we're going to try and so we want to minimize the integral of some function where x prime is u of t. So we want to sort of choose how should a ball roll down a thing to be the most efficient. That's one way to think of the problem. So what we'll do is we'll discretize we'll actually discretize the integral and discretize the differential equation using an approximate grid. So we're going to divide into 100 spots. We'll make a variable for each point on the grid. So we'll have a u and an x corresponding to each of those. So the dE can actually be written as a constraint. It's an equality constraint. So we'll use second order differences. You could use whatever order differences you wanted, as long as the only thing you'd have to restrict there is to keep it in line with how accurately you're doing the integration. But second order differences are quite adequate for this problem. So we set this equal to the u, so that effectively, so once we satisfy this constraint, we're satisfying the differential equation to within second order. Okay, so then, and also we have to put in some stuff at the boundary. Okay, so this is sort of the interior. Okay, the boundary. So we put in a special case at the boundary is that x of 0 is 1, and then so we handle the boundary there. And then we'll, for doing the integration, which is a second order rule for integration, we'll just use the trapezoidal rule, which is just u sub I plus u sub I plus 1 over 2. And we don't need to handle the special cases at the edge there because of the properties of u and x. Okay, and so then once we have the trapezoidal rule, well, this is the objective because that's the integral we're trying to minimize. Okay, and then the constraints are the DE constraints, basically, along with what we do for the boundary, and then that's it. So it's just a quadratic optimization. And these graphs on the web page didn't come out great. If you actually, get the notebook and plot them out, you'll see much nicer values. But here's x, so u is actually a linear, turns out to be a linear function. And so, and there's actually, you can find an exact solution, and so our solution comes very close to the exact solution for this. So that's another example of using quadratic optimization. So again, our modeling framework makes it relatively easy to do another step here, which in this case, this extra step is the discretization. If you had to write the quadratic optimization in terms of matrices, you'd have yet another step to get there. And so this provides additional convenience. Okay, so here's another type of quadratic optimization, okay, that's called second order cone optimization. And the idea is that instead of the objective being quadratic, some of the constraints are effectively quadratic. Okay, and in fact, those constraints are described in terms of norm constraints. So this constraint, okay, norm of something is less than or equal to something else, is what's sometimes called a Lorentz cone or second order cone constraint. And we have a function called second order cone optimization that handles these types of constraints explicitly. Okay, so we're actually writing some cone constraints. So what we want to do in this problem is we want to open up a bunch of, set up, a certain number of new factories, okay, and we need materials from another number of warehouses. And what we want to do is we want to optimize the location of the factories to minimize the transportation costs between the warehouses. Okay, so we sort of, the transportation costs are going to correspond to the distance, okay, and that's where the norm constraints come in, because this is the distance, and these variables d are the distances. Okay, so the warehouse locations are given. We talk about the costs from different warehouses might be different because there may be more traffic, or may be harder to get in and out of a certain warehouse. So we can have variable costs here. So eventually we set up, so we set up these constraints, which are these distance constraints. We want to minimize the total cost, which is the sum of the distances, and then that's it. We get a result out. We get what the distances are, and probably the most important thing which we're really trying to get out here are the distances, the locations of the two warehouses, and this can be shown on a graph. So the two factories. Okay, so these are the locations of the two factories that optimizes the distribution from these warehouses to these factories. Okay, so here's another second order cone optimization type problem, a quadratic problem, and this one is sort of a structural optimization. So suppose you have a set of a set of springs with masses hanging between them, and you want to find out what the actual shape of this spring is going to be. Okay, so what we're doing here is showing that there's using a minimum energy requirement can be equivalent to an optimization problem. So here we're going to take 20 springs. We're going to have just the gravity, calling that the potential energy. And then there's the spring potential energy is based on the spring constants. Okay. And then, so we're going to add another constraint so that the norm is less than or equal to the variable u, and then we put in conditions that the two ends of the springs are fixed, and then we condition the links. So basically, one spring is connected to another spring. In principle, you could probably do some sort of a network of springs this way, but of course that would be very complicated, and would involve sort of connectivity, sort of like what we did in that truss problem. So this keeps this relatively simple. We have some derived design parameters. So the total energy is going to be the gravity energy plus the spring energy. We want to minimize, so the minimum energy condition says we minimize the total energy. We minimize this total energy compared to the constraints, and we get something that, so given 2 points, we get this, and this shows how much the strings are actually stretched. And if you look on the in the source pages, you can actually get to a manipulate that shows you can move around the points, and the still problem works quite generally. Okay, so now we're going to get into something which seems a little more esoteric, but it's actually just another case that convex optimization works in. This is called semi-definite optimization. And basically, in semi-definite optimization, you end up with matrix, what are called matrix inequality constraints. And the classic matrix inequality constraints is that you have something like, I'll actually just show it here. You have lambda times identity is greater than or equal to a of xy. So what that means in a mathematical sense is that lambda times the identity matrix minus a of xy has to have all non-negative eigenvalues. That's what that constraint. So it's actually a constraint on the eigenvalues of the matrix, and that's often called a semi-definite cone constraint, or a linear matrix inequality is another way people express these. And so notice this is the same vector greater equal sign that I talked about before, but notice it has a subscript under it now, and that's s squared. And that refers to the semi-definite cone of dimension 2. Okay, and so S of 3 would be the semi-definite cone of dimension 3. So this means this one corresponds to 2 by 2 matrices. And so this actually works for matrices of any size. We're going to do 2 by 2 matrices to keep it. So what we want to do is we want to find this first problem we're doing is we want to minimize the largest eigenvalue of a matrix. Okay, so basically, if lambda is an eigenvalue of the largest eigenvalue of the matrix, then lambda times the identity minus a of xy, that's going to have positive eigenvalues. Okay, because if you broke a down as eigenvalue competition in an eigenvalue less than or equal to lambda, then that would not have positive eigenvalues. So we just write it as this simple problem. So we minimize val lambda, we minimize this semi-definite constraint, and then we get a value. And notice this is for a sum of a linear combination of different different matrices. And this is a very common type of eigenvalue problem that comes up with these. So we can show what the matrix is. We can actually show you, over different possible values of the x and y, what the eigenvalue is and the minimum. As you know, it's a very shallow minimum, but it is indeed a minimum. You can sort of check that's pretty close to what you get if you do this simple Monte Carlo simulation. And you can do other types of problems like this. So you could minimize the difference between the largest and the smallest eigenvalues using similar sorts of logic. You can minimize the largest eigenvalue, the largest eigenvalue by absolute value. That's sometimes called the spectral norm. And it works for combinations of any matrices of any size. Of course, if you get really big matrices, your solver is going to take a lot more time. But again, these convex solvers do reasonably well for reasonably large size problems. So a classic and a general nonlinear optimization method usually cannot handle too many variables because it sort of bogs down. But because we have this convex situation and we can use this, we can actually go to much larger size than a general nonlinear solver would be able to. So that's one big advantage of the convex setup. Here's another problem, and this shows another example of how we use semi-definite optimization. But the idea here is and this is a common thing done with the convex optimization, is you have a problem which is really hard. This is an example of a problem which is NP hard, and we do a relaxation of the problem. We say, okay, we're going to relax one of the conditions of the problem. And we can actually solve it in polynomial time instead of NP time. And we don't always have a certain solution, but in most cases, actually, the solution is quite correct. So here's a classic problem from graph called the max cut problem. So we want to find a subset of the vertices of a graph that divides the graph into two things that maximizes the weight of the vertices that are sort of connects the two subsets of the graph. Okay, and so basically, this involves using the Laplacian matrix of the graph, and so the exact max cut is to do this. Okay, so you find a max value. This ends up being theoretically correct, but incredibly slow, and you can only do it for very small graphs. Okay, so the solution, what we do is we construct a cut by max inverse random. So we decompose y into u and u transpose. Notice we're using that's the Cholesky decomposition. So we've done that. And then we find that's of the results. We do the semi-definite optimization, and so we get the result. And the relaxation here is that we've relaxed the rank 1 condition. We eliminate that, so we only require that y have positive eigenvalues. Okay, so we don't require that it be rank 1, and so that condition may be violated, but typically when you do it on a general graph, it doesn't get violated. So here's a bunch of examples where we find a max cut. So this is an example of a problem where we can't, for practical graph, it's NP hard, so we can't solve it generally, but we can get a solution which is good most of the time, and so that's a common thing. And actually, in coming version, there will be a graph function to get the max cut that uses this technique internally. Okay, so here's an example of a conic optimization problem. So I've talked about second order cone optimization and semi-definite optimization. Now, a generalization of all that is something we've named conic optimization. What that does is that optimizes a function based on a collection of specialized convex cones. And the convex cones that we deal with are the second order and semi-definite cones that I've already talked about. It also works with an exponential cone, a dual exponential cone, a power cone, and a dual power cone. So those are additional things. And the idea of conic optimization is you minimize a linear objective function, okay? And the constraints are that affine combination of the variables like ax plus bi, okay, have to lie in one of these convex cones. Now, it turns out another convex cone that we deal with is called the non-negative cone, and that's actually linear optimization is a specialized case of conic optimization where the cone is just the non-negative cone, which you can think of in 2D as the positive quadrant, in 3D the positive orthant, and in ND it's just where all the variables are, all the values are positive. So and that turns out to be one of these convex cones. Okay, so let's take, so we're going to find something called the analytic center. It's the x which minimizes the distance of a point x to the polyhedron to each side. So we want to find some x that minimizes the distance, the sum of the distances to the product of the distances to the sides. So here's something. This is a little bit of a trick. So linear optimization has the ability to get out linear constraint matrices. This is another one of these properties, and this actually sort of is a way to get to the code that converts this boundary region into a set of inequalities. Now, I haven't written these as inequalities. Well, actually, we've done this here. So those are the equivalent inequalities for this polygon. Okay, so we write those as inequalities. Now the objective is a product of that. So if we take the log of that, we can get a sum. So we take the sum of the log. Now the log function is concave, so the negation is convex. Okay, and so this is a convex function. And there's an important transformation that this is what allows conic optimization to handle. It only has to handle linear constraints, because if you have any convex function, you can say f of x, okay, you can replace that convex function as an objective with a new variable t, and the additional constraint that f of x is less than or equal to t. That's called the epigraph transformation. And it basically is replacing a convex function with a constraint that, something lie within a convex set. And so in general, you can always, in any of these convex functions, you can always specialize the case of a linear objective by using this epigraph transformation. So this is an example of doing that. Okay, so conic optimization, we want to minimize t, which is, we've replaced this with t. Okay, we have the, and the objective is less than or equal to t, and that's the objective. We've written as the sum of logs. Now it turns out the logs, log less than or equal to t, when it's convex like that, or minus log less than or equal to t, can be replaced by an exponential cone constraint. So this ends up being an exponential cone constraint problem. And this gives us the analytic centers. Okay, and these give, so this is an ascribed ellipsoid and a covering ellipsoid from the analytic center. This minimizes the distance. Okay, so another sort of geometrical type problem. that involves these things, involves more optimization components. So suppose we have a convex polyhedron again, and suppose we want to consider finding the largest cuboid we can actually fit inside of that that thing. And that would be given by cuboid. We're going to consider an axis-aligned cuboid. Okay, and so we want to minimize right. So we want to minimize. So basically, we're going to have, you know, S times these tuples. So the lengths of the sides are going to be the thing. So we're going to minimize the product of the length of the sides. Okay, so so it turns out, so this again is using some facts about convexity. Okay, so the product this is the same as producting convexing the geometric mean, which is the product to the 1 over n power. Okay, you can just take it to the 1 over n power, and that's concave. So maximizing this is the same as minimizing minus that, which is convex. So again, we can use this epigraph transformation. So we minimize minus t with this constraint. Okay, now this constraint ends up being a power, can be written in terms of a power cone constraint. Okay, so the power cone takes a parameter which is alpha, which is the power. Okay, we can write the constraints in a form like this using this power cone, and eventually we keep working and we can get to the solution of the problem. So we have, you know, basically for each dimension we have some power cone constraints. Is a general way of breaking it down. Now, I started with a convex polyhedron, okay, but actually the setup of the problem really only required that the inside thing be a cuboid so that I can set up those side lengths. But the outer set could be anything that is itself convex and representable by these convex cones. And actually, these convex cones are able to present a huge number of different convex functions. So they're not a complete covering of the space, but you know, with some figuring, it's often possible to represent just about anything with these, or approximately represent with these. So here we can do the same sort of problem, but instead we're using the ellipsoid. And here's the maximum cube that fits in an ellipsoid. And so, okay, so here's another ellipsoidal problem. And this is, so suppose I have a whole set of points, okay, and I want to find the largest ellipsoid that fits around those points. Okay, this is a problem that can be used. It's actually turns out to be a conic optimization problem, but what I'm going to show you here is that actually n minimize now is been given, sort of the more general minimization functions, has been given the power to recognize convex problems and automatically use the convex solvers when appropriate. So it turns out that the objective here is I want to minimize the log of the determinant of A, because the volume of the ellipsoid is proportional to determinant of the inverse of A, and the log of the determinant of inverse of A is convex. So we can do this with convex optimization. So here we set up, so we want to the condition that A be that this be an ellipsoid is simply that it's a semi-definite matrix with, you know, all positive semi-definite matrix. So we just have a semi-definite constraint here, and we have these, and then we have to deal with this log. But n minimize knows how to deal with this particular objective by doing because it recognizes it's contract, so it automatically does the transformations that are necessary. We get it, and you can see this is the ellipsoid that surrounds some set of points. Now there's a function in Mathematica, or Wolfram language, called, you know, bounding region, and there's a different types of bounding, and there's one called fast ellipsoid, and this is much faster than doing this. Okay, but as you see, it's giving you a quick result as opposed to the optimal one. So it gives you actually a somewhat bigger ellipsoid than you need to. So here's an example that shows, again, we're going to use n-minimize as an interface to convex optimization. Well, all we have to do is we have to be careful to put in, sort of make our constraints explicitly convex so that n-minimize can recognize things as convex. So what we're going to do is we're going to try and set up. So we're going to have a large rectangle. In fact, I'll show you the picture to give you a better idea of what we're doing. So we're going to have some large rectangle, which is a gray, and we want to put in a bunch of, say, workspaces or rooms or locations with a certain space in between them, so that optimizes the space users and minimizes the size of the big rectangle. Okay, and you can describe, basically what we do is we describe the relative location, so of places by a graph, and I'll show you a quick thing here that shows you the idea. So we have a horizontal graph and a vertical graph, and the horizontal graph says that this has to be to the left of this, and that sort of translates to certain conditions. And the vertical graph says this has to be below this. Okay, x of I has to be below x of I. And those can be translated using sort of these pictures almost directly into constraints. Okay, and I've written a function which is hidden here, how we translate to those constraints. But basically, once we do that, we have to make some of the constraints explicitly convex, and then there's here's a function which I'll show this plan for. Okay, so we have a bunch of positive. You can notice I'm using the full form of this vector greater equal rather than the notation, because this might be something you might want in a file to load the function. And it turns out to be semi-definite optimization. And the reason it's semi-definite optimization is the trick is I want to represent h times w, the height of the width. So each sub-box has to be greater than its given area. Well, I can represent that. If I just wrote that as a constraint, it's not obvious that it is a convex constraint. So what I can do is I can write it in a semi-definite form, and it turns out that this matrix condition, so h, w, a, and square root of a, having positive eigenvalues, is equivalent to this constraint. So that's a convex way of writing the constraint. So with that, then n-minimize is able to recognize the problem as convex, and it uses the efficient convex solvers to get a good solution. And you can sort of play around with different features of that. Okay, so here's another example of using n-minimize family of functions, general functions. So what we want to do is, so suppose we have a signal, and in this case, I've taken a signal which is just the Dow Jones Industrial Index. And suppose you want to smooth it to sort of, get rid of some of the features, but you want to preserve the structure as much as possible. Okay, so so what we're going to do is we're going to basically effectively do a fit to this signal. We're going to find kind of a model function that fits this signal. We're going to regulate. So what we want to do is we want to find an x that minimizes the norm of the signal, okay, plus the norm of the differences of the signal. So what we're trying to do is we're trying to minimize the norm of the. So not only are we trying to make s close to x, the given signal, okay, we want to minimize the norm of the differences. So we want the local variation to be as small as possible, but we also want to find the thing that balances those two things. And so that's the idea. So x is the original signal coming in, s is a smooth one, so we're using a difference. This is also sometimes called least variation regularization. Okay, and so we can do that, and we can find an approximate signal. What this does is you get the real dives from the financial crisis, but you're not getting sort of the local day-to-day variation, which is a convenient way to look at this. You can also change. So instead of using just one, you can use a lambda times the normative differences. You can find a kind of a trade-off right here at the bend is where you're getting sort of the best balance of trade-off. And so if we chose that, we actually get a slightly better graph. It kind of goes down to that much closer to that lower peak. And you can do a whole bunch of different ones. I mean, if you smooth too much, obviously you're going to get something which shows the dive, but nothing else. If you don't smooth enough, you get something in it. So there's a parameter. And actually, this has been built into fit through a new option called fit regularization. It's total variation. And so we can choose this, and that gives you the same value without having to directly use the convex optimization function. And so fit has actually been given quite a bit of new power via these convex optimization functions. Another example of where fit is quite powerful, and this is a fit regularization problem, but what we're going to do is, this is often called basis. This is a basis pursuit problem. And the idea is we have some enormous basis of functions, okay? And in this example, I think we have like 65,000 different basis functions. And we want to do a fit, but we only want to decide which are the best basis functions to use to actually get a reasonable fit, because we can't, in practical work, a model that uses 65,000 functions as a fit is not going to be very easy to work with. If you could reduce it to a whole bunch of numbers, you'd be better. So the idea is we set up this basis. These are called Gabor functions, and they have, they basically have a peak, and then they have variation, and there's levels. So basically, we're changing the Gabor function basis has different positions where it's centered and also different frequencies. Okay, and we go up to a certain number of frequencies and a certain number of bases. The idea is you want to, represent a signal quite well with this. So, so we can get a design matrix. We get a basis matrix, okay, which is a big matrix. So this is a 500 by 30,000 matrix with over 3.5 million elements, okay, that are non-zero. So that represents the basis as a matrix. Okay, so here's some signal which involves, both some sort of, smooth changes and then some sort of frequency underlying it. So that's going to be our discrete signal. So what we want to do is so fit now can directly take a basis matrix once you've set it up and a discrete signal. So this would be a least squares fit, okay? And so you can get a least squares fit with this basis quite well. The question is, but that ends up using essentially all 65,000 or 30,000 basis elements, which is not very effective. So the idea we want to do is we can use a fit regularization, which is called L1 regulation or lasso regularization. And what that does is it penalizes having more basis functions in some sense. And so it's a way of restricting the number of basis functions. And so basically, if we do this L1 fit with a L1 parameter of 1, so this is a little bit like the lambda I showed in the last problem. Okay, I wind up with just 53 basis elements instead of the 30,000. And we can show, and you can hardly tell the difference between the perfect least squares fit and my subdued basis function. There is a difference, okay, but it's relatively small. It's within like 6 or 7%. Okay, so we've cut down the number of elements tremendously. And what you actually want to do is once you determine the basis elements, you go back and do another fit with those basis elements, and actually that reduces the error significantly further. Okay, and you can play around with this value of lambda, and if we increase lambda, decrease lambda, we'll get more basis elements. We increase it, we'll get fewer basis elements. Okay, and you can kind of balance the error you're willing to. So by going to 65 elements, we're down to 0.005 in the error, which is quite small. If we go to too few basis elements, the error becomes somewhat more significant. So it's a balancing act. Okay, so that is the set of examples we have. There's lots of documentation. There's a huge number of examples in our documentation for the convex optimization solvers I've talked about. So if you look at those, and those are referred to by these pages. And I think that if you're interested in doing any kind of optimization problem, it will be useful to look at the new convex features and use those as much as possible. All right, well, thank you very much. And that's all I have to say.